Hi, I'm Andrew Freeman with UNC-Chapel Hill, and I will be presenting our work, Content Adaptive Rate Control for Surveillance Video with Event Cameras. So the motivation for our work is focused on this area of video triage, which can be very, very slow, especially if you're running complicated, complex analysis algorithms. So in particular with surveillance video, most of the image is not changing over time, especially with stationary cameras for surveillance video. A lot of the image is going to be the same over long periods of time, and there are just going to be small regions that are actually moving and therefore providing new information. So our big question here is, in traditional vision pipelines, why are we continuing to repeatedly process the parts of the video that are not actually changing very much? So our goal here is to make arbitrary computer vision algorithms faster by reducing the actual amount of input data that needs to be processed by those algorithms. So our particular application that we're focusing on in this work is fast feature detection, which stands for features from accelerated segment test. So this is a tried and true feature detector that is, like the name says, very fast, and it works by simply looking at a candidate pixel and a circle of pixels around that candidate to see if there is a contiguous streak of pixels that are all either brighter than the candidate by a certain amount or darker by a certain amount. And that is then classified as a feature. And you can use features for all sorts of things within computer vision, including tracking objects, tracking the motion of a camera over time throughout a scene. And it can also be used as sort of high-level metadata indicating the activity level of a scene. And our approach to trying to speed up this application is actually leveraging some prior work that we did through LAS in the development of an asynchronous video representation. So the idea here is that whereas with traditional video representation, you have a single frame that has a uniform sample rate for every single pixel. So you have a frame, it's an entire image, and you have a piece of data, a pixel value for every pixel within that frame. And this occurs at a regular frame rate, what we call it. Now, our system, which we call adder, on the other hand, is actually completely asynchronous. So you don't have image frames, but every pixel kind of reports data independently when it has reached a certain threshold of light that it has gathered. And what this allows you to do is have a very high data rate for the parts of the video that are actually changing quite a lot, and a much lower data rate where the video is stable. So particularly with surveillance video, when the camera is not moving, you can have, instead of a new update for a pixel 30 times per second, even if it's not changing, with adder you can get one update every 30 seconds or every minute or every hour if that pixel is actually not changing very much. So we're fundamentally reducing the amount of data that needs to be processed by a downstream vision application. So here's kind of the comparison pipeline for these two different systems. So with the traditional video pipeline at the top, you have raw image frames being produced by a camera. You're going to encode those with a traditional video encoder. You get really good compression performance, but then when you want to actually run vision applications on this data, you decompress it and have a large image frame on the other side. So lots of data being produced on the decoder side, and all of that data has to be processed by your vision algorithm, even if it's not really very different from the previous image that you already processed. Now, with our event-based system, we actually reduce the data rate of the video that is being compressed, so that when it is decompressed, we actually have very sparse information. So here in this example, we're only getting new updates for the pixels that are moving, the areas of the video that are actually changing, and that is the only data that has to be processed by our feature detector, by our computer vision algorithm. And we kind of illustrate that here. We're only detecting new features in this case, and then we can add those to previously detected features and get the identical result on the application side, while processing a lot less data. And our evaluation for this system, we looked at the Virot video surveillance data set. We analyzed 135 videos from that data set, and we measured things like the reconstruction quality of our video at various quality levels that our transcoder allows, the speed of the feature detection, and then the bit rate of the files produced. So here's an example of our GUI application for transcoding videos to our adder representation. And here I am running feature detection and illustrating that in different ways. And you can see here at the top, we track the PSNR in red over time. And as we sort of adjust different quality levels, you can see the PSNR go up and down. And then down here, we show the data rate. And basically, if we are below this blue line here, that means that the decoded data rate for a vision application is going to be less with adder than it is with the traditional video representation. And so some key results that we have to show very briefly are that we can actually achieve enormous gains in the computer vision application speed by using an asynchronous representation. So here we can see that at our lossless quality, adder is actually quite a bit worse, which makes sense because the data rate is actually much higher than a traditional video. But if we allow a little bit of loss, we can already start to see improvements in application speed. And at our lower quality setting, we can have a median improvement in feature detection speed of 35.5%, which is quite enormous. And you account for this at very large scales, thousands of cameras reporting video 24/7. A 35% improvement in application speed can also result in a 35% reduction in cost, computational costs. So we think this is a rather dramatic result. And then sort of the motivation behind that is here we see that in order to ensure that our application runs faster than the traditional frame-based application would be, we need to reduce the adder event rate such that there is one event for every 40 pixels in the image. And that can be a simple check, so you can make sure, if we are beyond that threshold, we can use our asynchronous feature detection. And if we are below that threshold, well, we can just use a traditional frame-based feature detector. And the system is completely transparent to that decision, and it's trivially easy to switch between those. So for future work, we can plan to continue to extend our system by adapting additional vision algorithms for this asynchronous paradigm, work to improve the speed of our transcoder with hardware acceleration, and then also to tune our compression and our algorithms for native event-based cameras, which was kind of the initial motivation for this work, is how can we also leverage these applications for event-based cameras and apply that in a surveillance situation. But this will also require us to gather a large-scale surveillance video data set with an event-based camera, which is something we plan to do down the line. So thank you for your time. I hope you enjoyed it.